Good morning, everyone. Today I will present our paper called entitled Reliability Augmentation of Request with Service Function Chain Requirements in Mobile Edge Cloud Network. This is joint work with Yuma, Wenzhen Xu, and Xiaohua Jia. Before we start, I outline today's talk. We start with motivation and challenge, followed by goal, preliminaries, and problem definition. Then we solve this problem, formulate an IRP solution. We then relax to the LT and derived or randomized algorithm for this problem. Certainly, this approximation algorithm with some resource constraints violation. Later, we develop a fast heuristics algorithm without any resource constraint violation. We also conduct performance evaluation. In the end, we give conclusion for today's talk. First, we talk about what's called mobile edge computing. Mobile edge computing provide abundant computing and storage resource for mobile user at the network edge. It has been proposed to respond to delay-sensitive applications in which cloudlet are co-located with access point. Thus, the quality of service and the energy consumption of mobile device can be significantly improved. On the other hand, network function virtualization has also been proposed to implement the network function as software components in cloudlet. Such doing, can introduce a new dimension cost saving on hardware with boxes, make it, the new network function enable flexible, faster deployment. So, how to mobile edge computing and network function virtualization combined together. This has been envisioned as a key-level technique to support delay-sensitive application in smart cities, IoTs, and intelligent transportations. So one important problem is network service reliability. Network service providers provide mobile user with low latency, high reliable network service through the placement of services VNF instance to cloudlet in MEC to meet the user demands. You already have service function chain and reliability expectation requirements. Due to the chain nature and the distributed placement of VNF instance, the failure of any VNF instance in the chain will heavily affect the normal operation of our service and will result in serious data loss and service failure. So redundancy backup is a common practice to improve service reliability. That is redundant placement of VNF instance to cloudlet as backups. Augmenting the service reliability of an omit request poses several challenges. One is the computer resource constraints on each cloudlet in the network is limited. Each request have source function chain and reliability requirements. How many secondary VNF instance of each primary VNF instance in the service function chain can be instantiated. Which cloudlet will this VNF instance be placed to if there are no air hops of the cloudlet accommodating this VNF instance from the primary VNF instance. The main contribution of this paper, we formulate a lower service reliability augmentation problem for an omit request. We show the problem is NP hard. We propose a low travel integer linear programming solution to the problem. We develop a randomized algorithm with a provable approximation ratio for the problem with high probability, However, this is achieved at the expense of moderate violation of computing capacities on cloudlet. We also design efficient algorithm for the problem without any resource violations. We finally evaluate the performance of a proposed algorithm through experimental simulation. Experimental results demonstrate the proposed algorithms are promising compared with the upper bound of the optimal solution. Here is the network. In this network, we have 6 switches. In some access point, you have cloudlet located, co-located cloudlet. In here, you have 4 nodes have co-located cloudlet. Each cloudlet you have a computing capacity. So we consider requests come in one by one. Now we consider the request J. Let us if the J is in the social function chain of request chain. So you have F1, F2, FLJ, different network function. Well, the reliability of a particular network function instance we put as RI, small RI. So certainly this is between 0 to 1. Okay, if a request RGA is omitted, then the primary VM for instance on this FA source function chain have been replaced. The service reliability should be the product of this source function chain is right, I from 1 to LJ. So if there have reliability source expectation, rho J, if this one no less than rho J, that's enough. But in practice, this value is rigorously less than rho J. So we need argument is reliability as much as possible. Certainly our final goal should be reaching the expectation service reliability is the rule. Okay, so suppose we assume there have NI with instance for particular network function Fi, that there are reliability at different cloudlets, they have different reliabilities. So the accumulated reliability are capital Ri of AFI in this chain. Suppose it's 1 minus product I from 1 to Ni. Ni is the number of instances you try to induce. We assume the software implement at any cloudlet is the same probability. So to simplify problem, then we got a UJ means the entire service reliability should be the product I from 1 to LJ, the RI. All right, to ensure the reliability rho J of RJ can be achievable, we must have nays, right? Equivalent, you both sides you use logarithmic, then this become looking like nays. So originally we're trying to maximize nays. Now we're trying to minimize nays. So now we can formally define the problem. You give MUC network, each cloudlet you have capacity, you have a set of functions, each function has a resource demand, and each function has a reliability. So the question is, we tried to, we call the service reliability augmentation problem for an immediate request J. That means each primary VF instance has been allocated in a cloudlet. All of its secondary VF instance should be located in cloudlets, not far from the primary one, maybe it's up to L. So make a list, we tried to say reliability, middle is reliability expectation, or, best possible because you do not have enough resources to achieve the expectation. So for the initial admission framework, that means given a request that you try to put the primary service chain and doing this. This is quite easy. We put this as a dead. This is a source, this virtual destination. This is all cloudlets, who with the F1 the computing demands still lift. Then this is the second layer is F2, for this one, and so on. In the end, if you're able to find a path from SJ to TJ, then this is implied, in certain cloudlet, you can install this primary VNF instance. Because of the time issue, I cannot go much more detail about that. Now we basically just say, we already, implement the primary VNF instance already. Now we try to augment the rest secondary VNF instance, making this service as reliable as possible with the aim to achieve rho J is reliability expectation. What do? We reduce the problem to the service reliability augmentation to the budget minimum cost generalized problem. So what's the generalized problem? Suppose you have n being indexed 1 to n, with each being bj is the capacity. They have n terms. Each term have a positive cost, Cij, if with size Sij, if this item is packed by bin to bin j. Suppose the total cost is given C. The gap problem is you pack as many items as possible to the M bins such that the total cost is minimized, and certainly the cost is upper bound by C. Okay, so let's have a look. We assume each use C prime the base V as the residual computing resource at cloudlet V. Let Ki be the maximum number of secondary VM instances of I can be placed in one multiple cloudlets. So suppose V is a primary VM instance Fi. So the rest secondary only able to play in the N plus L, that means the L neighborhood of V. For each VM instance, that we already know that maximum Ki items. So we try to figure out how many of items should be replaced. We use CFI KIU if place bin here. We treat each of these liberal cloudlets as a bin. Otherwise, it could incur the large cost. M is defined cost because we try to minimize the total cost. So the cost definition basically for this particular function, if you have K, signal replaced, then you calculate the accumulated cost minus, if you K minus 1, we have the instance. So then you use logarithmic. From here, we can see this problem is, we try to pack as many as items. Now, item actually is a VNF instance. The budget is this one. Also, each cloudlet you have the residual energy C prime V. So this is the integer linear program for that. This is maximize. Minimize the related service reliability is log minus log Ri. So this is certain conditions. This basically say is achieved. For each Fi and X request, KIFI, Fi belong this one should be only one. This is each cloudlet, the capacity should be satisfied. So for that case, we already know that Fi if VM, for instance, KVM for interpolate to row, that's must cause a larger zero. If not, you use larger than that, then this one, because you play more redundancy, you get a more reliable. So this is always true. Give an exact solution to the IRP. We claim if ki star equal 1, where ki is the largest value in the solution that no greater than the upper bound of the number of signals ki, then this in here you may be multiple one, so you only choose one as equals 1. The probability, the rest is you just for the rest you put a 0. So here we got the IRP solution. First, you find a solution, solve the IRP, then relaxation to LP, and then this is IRP optimal solution, because this solution is a fractional. So an integral solution by randomized rounding, that means a particular variable is set to 1 with the probability is not this. Otherwise, the probability is 0. The choice between this one is a little bit challenging. Yeah, if you're doing further analysis, a candidate, the integer solution can be derived based on xk, xi, kiu. Now we're trying to analyze the running time. So the algorithm will be, succeed with a high probability. This is 1 minus 1 after n. N is the number of all of the backup, VM, for instance, different one. 1 minus 1 after 1 over v square means this when n approaches infinity, this two approaches infinity. So this the value becomes 0. Then you only one choice. So we got the probability is 1 after p star 2 to 1 minus 2 to lambda. So the rest is quite easy, just to follow that. The algorithm we introduced, is approximation algorithm with probe approximation. But unfortunately, because they have some, resource violation. If we do not allow resource violation, what do? We give a heuristics algorithm. The basic says arguments and the reliability request through construct of, a series by parity graphs. For each bipartite graph, you try to find the minimum cost maximum matching from the current graph, which corresponds a subset of secondary VM instance to the matched clouded without violating the computing resource of any sort. So the algorithm basically say, follow the optimization objective. We aim to increase the reliability of request J by placing as many as secondary VM, for instance, as possible to cloudlet and minimize the placement subject, the cost budget and the computing budget are combined. To this end, we conduct a series auxiliary bipartite graph. We start with graph 0 as follows. V is the residual computing capacity. I is a set of all possible VNF instance VNF. Okay, so looking like this. There I have an age between them, and this with cost is similar like we defined. Now we're trying to analyze the running time. The running time is, by the algorithm, is look like this. Is quite large. So I do not want to talk too much about that. So we also conduct the experiment with, because time constraints here, I just talk about a little bit about it. So in terms of the run times, you can, the performance and ILP, is the blue one. The red one is randomized. Sometimes better than ILP in the best solution. The reason behind is because of resource violation. So this one is about the randomized user confidence ratio. The typical is 1 and above. That's very amazing. Finally, we talk about that's just the single one. If you talk about a set one, you maybe also can say our algorithm significantly is running larger than these algorithms. Okay, so we finish that. In the end, we conclude we start a lower reliability augmentation problem for a mid request with requirement. We show the problem in NP part. We divide efficient or randomized and heuristics algorithm. We conduct experiment. Have any other questions?